Good day everyone, I'm Engineer Rodrigo Pimillares. Today we will discuss about the introduction to the course and mathematical proofs with these following students.
Introduction of the course in abstract algebra. Definition of abstract algebra. Abstract algebra, a branch of mathematics in which algebra concepts are generalized by using symbols to represent basic arithmetical operations. Abstract algebra course introduces students to advanced mathematical concepts such as a group theory and lattices in algebra, which is a broad division of mathematics. Abstract algebra is the study of algebra structures. Algebra structures include groups, rings, fields, modules, vector spaces, and lattices and algebras according to Wikipedia. Abstract algebra background. Necessary in the study of abstract algebra: basic knowledge of the set theory, mathematical induction, equivalence relations, and matrices. Ability to read and understand mathematical proofs. Differences of abstract algebra from elementary algebra. In abstract algebra, algebra structures such as groups, rings, fields, and axiomatically defined and investigated. Abstract algebra extends the familiar concepts found in elementary algebra and arithmetic of numbers to more general concepts. There are frequently asked questions related to abstract algebra. What is the use of abstract algebra? Abstract algebra is used in many fields in mathematics and science. For instance, algebra topology uses algebra objects to study topologies, and ability to read and understand the mathematical proofs. What are the differences of abstract algebra from other sciences? In laboratory sciences such as chemistry and physics, scientists perform experiments to discover new principles and verify theories. In studying abstract mathematics, we take what is called an axiomatic approach. That is, we take a collection of objects S and assume some rules about their structure. Abstract algebra useful. Some abstract algebras, particularly group theory and Boolean algebra, have enormous practical uses. Abstract algebra is useful because it provides another way to look at the same problems of classical algebra that could always provide different insights to the same problems. What are the differences of abstract algebra from other related fields in algebra? Abstract algebra is the study of operations, their properties, and the structures that supports them. The first operation that was ever learned probably was addition of natural numbers. Later, zero is included the negative numbers and started solving integer equations given x plus 7 is equal to 3. What is x? Abstract algebra asks a higher level question. Under what condition does a solution exist? The first algebra structure to study is the group, the simplest setting in which a unique solution to an equation is guaranteed. What are the roots of abstract algebra? The roots of abstract algebra are found in the late 18th to 19th century, with particular concrete investigation into geometry, number theory, and polynomial equation. It was not realized until the second half of the 19th century that several different areas of study all fit under the same umbrella of abstract group theory. The first to take this completely abstract perspective was Arthur Cayley in 1954. Here are some examples of algebra symbols: equivalence, floor brackets, ceiling brackets, function of x, open interval, close interval, set, infinity, cube root, and square root. Those are the algebra symbols.
Hi, I am Rizani Nial from BSIT 1B and I will be reporting about fundamental concept and abstract algebra. So we have sets, binary operations, identity elements, inverse elements, associativity, and commutativity. Sets. Rather than just considering the different types of numbers, abstract algebra deals with the more general concept of sets, a collection of all objects called elements selected by properties specific for the set. So, all collection of the familiar types of numbers are set. Other examples of sets include the set of all 2 by 2 matrices, the set of all second-degree polynomials. Example is ax squared plus bx plus c, the set of all 2-dimensional vectors in the plane, and the various finite groups such as the cyclic groups, which are the groups of integers modulo n. Set theory is a branch of logic and not technically a branch of algebra. So I have here the example of sets. So a set of numbers 1, 2, 3, 4, a set of letters A, B, C, D, and a set of names Rizani, Nico, and Berna. So all of these are called set because it is a combination of elements. So next is binary operation. So binary operation is a rule for combining two elements called operands to produce elements. The notion of addition is abstracted to give binary operation star say. The notion of binary operation is meaningless without the set on which the operation is defined. So we have addition, subtraction, multiplication, and division. It can be a binary operation when defined on different sets, as are addition and multiplication of matrices, vectors, and polynomials. So for two elements A and B in a set S, A star B is another element in the set. This condition is called closure. So for example, our A and B here is our operand. So when able to combine it together, we need to use binary operation, which is the addition, to produce another element which is A plus B. Identity element. The element of a set of numbers that when combined with another number in a particular operation leaves the number unchanged. So the numbers 0 and 1 are abstracted to give the notion of identity element for an operation. 0 is for the identity element for addition and 1 is for the identity element for multiplication. For a general binary operator star, the identity element E must satisfy A star E equals A and E star A equals A, and is necessarily unique if it exists. This holds for addition as A plus 0 equals A and 0 plus A equals A, and multiplication A times 1 equals A and 1 times A equals A. So, not all sets and operator combination have identity element. For example, the set of positive natural numbers, for example 1, 2, 3, has no identity element for addition. So, a set R is said to have identity element E with respect to a binary operation star if for every element A set R, A star E equals E star A equals A. So, for every binary operation, what we are trying to say is that if element in a set R is combined, an element, identity element, and then binary operation star, the result is still A. So, for addition, A plus 0 equals 0 plus A equals A. So, our identity element here is 0. So, A plus 0 equals A. So nothing changed about the result. So our identity element here is 0. So for multiplication, a times 1 equals 1 times a equals a. So as we observe, nothing changed about the result. So our identity element here is 1. Inverse elements. It is another element in a set that when combined on the right or the left through the operation always give the identity element as the result. The negative numbers give rise to the concept of inverse elements. For addition, the inverse of A is written A, negative A, and for multiplication, the inverse is written as A inverse. A general two-sided inverse element, A inverse, satisfies the property that A star A inverse equals E and A inverse star A equals E, where E is the identity element. A star A inverse equals A inverse star A equals E. So our E is 0 because it is the identity element for addition. So A plus A inverse equals A inverse plus A equals 0. A inverse plus A equals 0. A inverse equals negative A, so that A plus negative A equals 0 for our identity element. Associativity. It is a property of binary operation, which means that rearranging the parentheses in an expression will not change the result. Addition of integers has property called associativity. That is, the grouping of the numbers to be added does not affect the sum. So, for example, open parentheses 2 plus 3, close parentheses plus 4 equals 2 plus open parentheses 3 plus 4, close parentheses equals 9. Because 2 plus 3 equals 5 and plus 4 equals 9. So, in general, it could be open parentheses A star B, close parentheses, star C equals A star, open parentheses B, star C, close parentheses. This property is shared by most binary operations, but not subtraction, or division, or octonion multiplication. Commutativity. Commutativity property states that you can move numbers around and still arrives the same answer. Addition and multiplication of real numbers are both commutative. That is, the order of the numbers does not affect the result. So for example, 2 plus 3 equals 3 plus 2. In general, this becomes A star B equals B star A. This property does not hold for all binary operations. For example, matrix multiplication and quaternion multiplication are both non-commutative. So, for example, 4 plus 5 gives 9. 5 plus 4 gives also 9. So, even though there's a movement happen in the numbers, it still gives the same answer, which is 9.
Hi, I'm J. Marsibla, and now I'm assigned to discuss the definition of some related terms. The rules being assumed are called axioms, and using the axioms for S. Other information about S can be derived by using logical arguments. It is required that our axioms be consistent, that is, they should not contradict one another. Also, that there not be too many axioms. A statement in logic or mathematics is an assertion that is either true or false. Examples. First, 3 plus 56 minus 13 plus 8 over 2. Second, all cats are black. Third, 2 plus 3 is equal to 5. 2x is equal to 6 exactly when x is equal to 4. Fifth, if ax squared plus bx plus c is equal to 0 and a is not equal to 0, then x is equal to negative b, positive negative square root of a b squared minus 1ac over 2a. 6. X cubed minus 4x squared plus 5x negative 6.
mathematical proof, a convincing argument about the accuracy of a statement should contain enough details to convince the audience. If more detail than needed is presented in the proof, then the explanation will be either long-winded or poorly written. If too much detail is omitted, then the proof may not be convincing. Hypothesis and conclusion. If P then Q, where P and Q are both statements, if certain statements are known or assumed to be true, it can also say about other statements. Statements say nothing about whether or not the hypothesis is true. However, if this entire statement is true and it can be shown that the ax squared plus bx plus c is equal to 0 and a is not equal to 0, then the conclusion must be true. A proof of this statement might simply be a series of equations. The above series of equations is the derivation of the quadratic equation. Here, should not be equal to 0 so that it will not make the value of x undefined. Remember that any number divided by 0 is undefined. So this is the process on how to get the value of x. So this is the hypothesis and this is the conclusion, or in other words, the formula of quadratic equation.
So, good morning guys. I am Joven Jan J. Dinoy from Group 5 in BSIT Algebra. So, today I will explain to you what is proposition and not proposition. So, first, let me explain to you the proposition. A proposition is a complete declarative sentence that is either true or false, but not both. So, examples. There are some examples of proposition. So, a carabao has a four legs. So, it's true. Then, water is wet. Is true. 2 is an odd number. Is false. John has 31 days. False. Zamboanga del Sur is a province of the Philippines. Is true. So, let's proceed to the not proposition. So, there are followings that are not proposition. So, he is good in mathematics. She is 16 years old. He is balikbayan. So, there are given following as not proposition. So, letter A, it is time. Letter B, pay attention to this. Letter C, x plus 1 equals 2. And letter D is x plus y equals z. So, let me explain to you what are the givens. So, sentence A and B are not proposition. They are not declarative sentence or statement. And sentence C and D are not proposition. They are neither true or false since the variables have no assigned values yet. So, connectives and compound propositions. So, what is connective and compound propositions? Connectives are used in symbolic logic. Then, the proposition are given with symbols such as P and Q. So, what is propositional connective? Is a operation that combines two propositions to yield a new one whose truth value depends only on the truth values of the two original propositions. So there are examples. So basic logic connectives, and or not. Other logical connectives: conditional, be conditional, exclusive, or they can be represented by means of the basic connectives. So there are uh, table of propositional connective. So there are tables. So like this. As you can see, there are connective pronouns, symbol programming, and symbol in logic. So there are symbol like negation, conjunction, disjunction, conditional, biconditional, and exclusive or. And in the pronouns, and not, and, or, if, then, if any, only if, either, or but, not but. In symbol in programming, in and symbol and two. And symbol in logic, as you can see, I don't know. Okay. Then for symbol and reading, there are table. As you can see. So for the symbols, there are up and down, then right arrow, then left right hand side arrow, then reading for reading and or implies if then equivalent of and they if not. So let's proceed to compound proposition. So proposition build up by combining proposition using propositional connectives. So illustrative example. Today, for example, today is Wednesday. So that is letter P. And letter Q is it's raining outside. So that is the given example. So this is the solution. So PQ upper, today is Wednesday and it's raining outside. So then and P R and down, then Q, today is Wednesday or it's raining outside. So there are the sentence are different. Then P left I right arrow, then Q. So if today it's Wednesday, then it's raining outside. So then P right left arrow, Q, today is Wednesday if only and only if it is raining outside. So then last is P. Today is not Wednesday. So the sentence are have a different one because of the symbol and reading and connectives and compound prepositions. So last is quantified statement. So a quantified statement is one of the that says something about all some or none of the objects in a collection. So this is my end of my report. So thank you.
Illustrative examples. Number 1. All students in the college are taking history. Number 2. Some students are taking mathematics. Number 3. No students are taking both mathematics and history. Then, equivalent statements. In any language, there are many ways to say the same thing. The different linguistic constructions of a statement are considered equivalent. Illustrative examples. And number 1, all students in the college are taking history. Every student in the college is taking history. Number 2, some students are taking mathematics. At least one student is taking mathematics. Negating quantified statements. The negation of a statement all about all objects is not all. Not all can often be expressed by some are not. Example, all students in the college are taking history, and some students in the college are not taking history. Truth table. Truth table is a scheme for recording all possible values that may be assigned to a given proposition and to any new propositions that may be formed from them with the use of the connectives. Truth table of logical conjunction. A conjunction is a type of compound statement that is comprised of two propositions, also known as simple statement joined by the AND operator. The symbol that is used to represent the AND or logical conjunction operator is AND. It looks like an inverted letter V. If we have two simple statements P and Q, and we want to form a compound statement joined by the AND operator, we can write it as P and Q. P and Q is read as P and Q. Remember, the truth value of the compound statement P and Q is only true if the truth values P and Q are both true. Otherwise, P and Q is false. Notice in the truth table below that when P is true and Q is true, P and Q is true. However, the other three combination of propositions P and Q are false. Number 2, truth table of logical disjunction. A disjunction is kind of compound statement that is composed of two simple statements formed by joining the statements with the OR operator. In a disjunction statement, the use of OR is inclusive. That means one or the other or both. The symbol that is used to represent the OR or logical disjunction operator is V. It is resemble the letter B of the alphabet. Two propositions P and Q joined by OR operator to form a compound statement is written as VVQ. PVQ is read as P or Q. Remember, the truth value of the compound statement P and P or Q is true if the true value of either the two simple statements P and Q is true. Moreso, P or Q is also true when the truth values of both statements P and Q are true. However, the only time the disjunction statement P or Q is false happens when the truth values of both P and Q are false. Number 3 is truth table of logical implication. An implication, also known as a conditional statement. It's a type of compound statement that is formed by joining two simple statements with a logical implication connective or operator. The symbol that is used to represent the logical implication operator is an arrow pointing to the right, thus a rightward arrow. When two simple statements P and Q are joined by the implication operator, we have P rightward arrow to Q, where P is known as the hypothesis, where Q is known as the conclusion. There are many ways how to read the conditional P right forward arrow to Q. Below are some of the few common ones. P Q is read as P implies Q. P rightward arrow Q is read as if P then Q. P rightward arrow is read as P only if Q. P rightward arrow Q is read as if P is sufficient for Q, and etc. Remember, the truth value of compound statements P implies Q is true when both the simple statements P and Q are true. Moreso, P implies Q is always true if P is false. The only scenario that P implies Q is false happens when P is true and Q is false. Then the last one is truth table logical biconditional or double implication. Double implication, also known as biconditional statement, it's a type of compound statement that is formed by joining two simple statements with the biconditional operator. A biconditional statement is really a combination of a conditional statement and its converse. The biconditional operator is denoted by a double-headed arrow. When you two simple statements, also known as molecular statements with the biconditional operator, we get P double-headed arrow Q. P double-headed arrow Q is read as P if and only if Q, where P is known as the antecedent, where Q is known as the consequent. Remember, the truth value of biconditional statement P if only if Q is true when both simple statements P if only if Q are both true or false, otherwise P if and only if Q is false. Cautions and recommendations in proving propositions. A theorem cannot be proved by example. However, the standard way to show that a statement is not a theorem is to provide a counterexample. Then, quantifiers are important. Words and phrases such as only, for all, for every, and for some possess different meanings. Never assume any hypothesis that is not explicitly stated in the theorem. You cannot take things for granted. Suppose it is to show that an object exists and is unique. First, show that there actually is such an object. To show that it is unique, assume that there are two subjects, say R and S, and then show that R equal to S. Sometimes it is easier to prove that contrapositive of a statement. Proving the statement if P then Q is exactly the same as proving the statement if not Q then not P. Although it is usually better find the direct proof of a theorem, this task can sometimes be difficult. It may be easier to assume that the theorem that you are trying to prove is false and to hope that in the course of your argument, you are forced to make some statement that cannot possibly be true. Reminder: remember that one of the main objectives of higher mathematics is proving theorems. Theorems are tools that make new and productive applications of mathematics possible.
Good day, sir. I am Stephanie Dilarmente, BSIQ1B. I am going to discuss the proof. Proof is a convincing argument that some mathematical statements is true. A mathematical system consists of axioms, definitions, and undefined terms. An axiom is assumed true. Definitions are used to create new concepts in terms of existing ones. Undefined terms are only defined implicitly defined by the axioms. Within a mathematical system, we can derive theorems. A theorem is a proposition that has been proved true. A lemma is a special kind of theorem that is not usually interesting. A corollary is a theorem that follows quickly from another theorem. Euclidean geometry is an example of mathematical system. Example of an axiom in this system. Given two distinct points, there is exactly one line that contains them. The terms points and line are undefined terms that are implicitly defined by the axiom. Example of a division. Two angles are supplementary if the sum of their measure is 180 degrees. If two sides of a triangle are equal, then the angles opposite them are equal. A corollary is, if a triangle is equilateral, then it is a equiangular. Theorems are often of the form theorem 1, and we can see here in the screen, and this in a universally quantified statement is true, provided that the conditional statement. Direct proof. To prove that theorem 1 is true, we assume that 1 x squared, and xn are arbitrary members of the domain of this course. We also assume that px1 and x squared and xn is true. Then using px1, x squared, and xn as well as other axioms definition are previously derived theorems, we show directly that qx1, x squared, and xn is true. We will give a direct proof for the following statement. For all real numbers d1 and d squared and x, we will assume that d1, d squared, and x are arbitrary real numbers. We will assume that. Here you can see in the screen also from the definition of minimum, it follows that here. Then here are the indirect proof and proof on how we can get them. This special case of proof is called proof by contrapositive deductive reasoning. The process of drawing a conclusion from a sequence of propositions is called deductive reasoning. For example, the bug is either in Module 17 or on Module 81. 2. The bug is a numerical error. 3. Module 81 has no numerical error. If these statements are true, it is reasonable to conclude that the bug is in Module 17. The given propositions are called hypotheses, and the proposition that follows from the hypothesis is called conclusion. Valid argument. Any argument of the form if p1 and p squared and pn, then q can be written as a sequence of propositions.
My name is Ronel O. Parami.
Let's move to the valid argument. Any argument of the form if P1 and P2 and Pn, then Q can be written as a sequence of proposition. The proposition P1, P2, and Pn are called the premises or the hypothesis, and Q is called the conclusion. The argument is valid provided that if P1 and P2 and Pn are all true, then Q must also be true, otherwise the argument is invalid or a fallacy. Determine whether P implications Q, P equals therefore Q is valid. Proof. Suppose that P amplification Q, and P is true, then Q must be true, otherwise P amplification Q must be false. Therefore, the argument is valid. Let's proceed to the rules of inference for the propositions. To make sure that the intermediary conclusions are valid, each conclusion has to be deduced using some of the rules of inference listed below. There are 7 rules of inference, and the first one is P amplification Q and P therefore Q, and that's called modus ponens. And the second one is P amplification Q and negation Q equals therefore negation P, and that's called modus tollens. And the third one is P equals therefore P or Q, and that's called addition. The fourth one is P or Q equals therefore P, and that's called simplification. The fifth one is P and Q equals therefore P or Q, and that's called conjunction. And the sixth one is P amplification Q and Q amplification R equals therefore P amplification R, and that's called hypothetical syllogism. And the last one is P or Q negation P equals therefore Q, and that's called disjunctive syllogism. Let's proceed to the some examples of arguments. The first example is, if I study hard, then I get S. I study hard. Let P, I study hard, and Q, I get S. If I study hard, then I get S. I study hard. The result is P amplification Q and P equals therefore Q. This argument uses the modus ponens, therefore it is valid. Number 2 example, let's have the argument, if I study hard, then I get S. I do not get S, therefore I do not study hard. The result of P amplification Q and negation Q equals therefore negation P. This argument uses the modus tollens, therefore it is valid. Let's have the argument, I study hard, therefore I study hard or I will get rich. The result of P equals therefore P or Q. This argument uses the addition rule of inference, therefore it is valid. Let's have the next argument, I study hard and I get S, therefore I study hard. So the result P or Q equals therefore P. And this argument uses the simplification rule of inference, therefore it is valid. Let's have the fifth example of argument. I study hard, I have S, therefore I study hard and I have S. So the result P and Q equals therefore P or Q. This argument uses the conjunction rule of inference, therefore it is valid.
Hi, I'm Nanette Kunde. For the continuations of the discussions about the mathematical proofs, I am the one to continue and report about that topic. So now let's begin. This argument uses the conjunction rule of inference, therefore it is valid. Let's have the argument. I study hard or I get ES. I do not get ES, therefore I study hard. So this is the equations. This argument uses the disjunctive syllogism rule of inference, therefore it is valid. Rules of inference for quantified statements. There are four rules of inference for quantified statements. Let let x be a universally quantified variable in the domain of discourse D such that p of x is true. These are the four rules of inference for quantified statements. So these are the example rules of inference universal instantiation, universal generalization, existential instantiation, existential generalization. Everyone who is taking CS124 wants an A. Let's deal with the domain for all students taking CS124. P of X wants an A. For all X belongs to D, P of X. Jan belongs to D, therefore P Jan is true. Universal instantiation. P of D for any D and D for any student D in CS124, P of D is equal to D once and A is true. For all X belongs to D, P of X. Some students taking CS124 lab groups. Let D be the domain for all students taking CS124. Let Q denote the proposition X labs groups. We can rewrite this as exists X belongs to D Q of X. This means that we can find at least one student D in CS124 for which Q and D is true. Q of D is true. Conversely, if we can find at least one student D in CS124 for which Q of D is true, then exists of X belongs to D, Q of X is true. Combining the propositional and quantified statement inferences. Let's have one. Everyone loves either MSDUS or Unix. Lynn, number two, Lynn does not love MSDUS. Show the conclusion Lynn loves Unix follows from the hypothesis. Let P of X denote the propositional function X loves MS-DOS. Let Q of X denote the propositional function X loves UNIX or Unix. The first hypothesis can be rewrite as for all X, P of X or Q of X. By universal instantation, we have P lin or Q lin. The second hypothesis is Lin does not love MSDOS and Lin love MSDOS or Lin love Unix. Lin does not love MSDOS. Lin loves Unix by disjunctive syllogism. Therefore, the conclusion follows from the hypothesis. Quantifiers and logical operators. So these are the examples of quantifiers and logical operators.